Many real-world systems are affected by friction. Anytime two objects are in contact and experience a load that causes one to want to slide past the other, friction needs to be considered. In many cases, the other applied loads are so large that friction can be neglected. For example, in a frictionless pulley, the internal resistance to rotation is quite small compared to huge loads that are acting on the rope and cable, and so we get to leave it out. This video focuses on systems that can be modeled as particles that are experiencing friction, and to be exact, we're talking about something called dry friction, which means that we are looking at friction in systems without any lubrication. That's the topic of fluid mechanics or a tribology course, which is way beyond what we're going to handle here. With dry friction, the friction force is found using one of two coefficients, either the coefficient of static friction, which we write as mu s, static friction, or the coefficient of kinetic friction if it's sliding, kinetic friction. And unfortunately, this is one of those times where the physicists and the engineers disagree on terms. And so static friction, I'd rather call it stationary friction because, as we know, static systems are systems that don't accelerate. They can be moving at constant velocity. So really, we can have a static system that is sliding as long as we're applying the force to keep it moving at the same speed. Then we'd still have to use this kinetic friction. Usually, I can spell. Usually, the kinetic friction coefficient is much smaller than the static friction. In other words, it takes more effort to get something moving than it does to keep it going. Also, keep in mind we're going to need a table of values for the different values of this coefficient because it depends on the surface finish and the material. For example, there's a specific coefficient of static friction for stainless steel sliding on wood, and every other combination that you can possibly think of. To calculate the friction force, we're going to use the following formula. F sub mu, to indicate that that's our friction force, is equal to Fn times mu. And remember, we've got two different coefficients. So for something that isn't sliding, not sliding, this could be a system like a block sitting on a table. And if we push on the block with some force F, there could be a friction force pushing back that looks like F mu, and that is modeled as the normal force times the static friction coefficient. What's the normal force? Well, this block has some weight acting down, and there is a normal force in reaction to that, which we'll call Fn acting up. And so you can see those two things are linked. If this were sliding instead, now what we would have is a situation where this block, still moving along a surface, but it's got some velocity. Now we're pushing on it enough to keep it moving, which means that the coefficient of kinetic friction is needed, mu sub k, and we still have the same deal where we have to handle the fact that there's a normal force, which, at least in this particular problem, depends on the weight, Fn. So what I'd like you to do is I'd like you to think of friction. Think of friction as another reaction force. Because really that's what it is. And that means that to solve any problem involving friction, all we need to do is add this as another reaction force on your free body diagram, model it using F mu is equal to Fn times mu, either coefficient of static or kinetic, depending, and you're done. So just let's look at an example here. Imagine that I take a block and I put that block on a ramp. We know that this block has some weight to it, and that the ramp offers a normal force, Fn, a reaction force. But in order for this to stay static, or stationary I should say, we need a friction force acting up to oppose it, F mu. And we know that that F mu is the normal force times coefficient of static friction mu s. And what I want you to see here is that this normal force shows up in the model for the friction force, and it shows up here. And so when you sub this into the force balances, it actually eliminates an unknown. So that's really handy. We're going to deal with 3 different types of friction problems. A type 1 problem, if you will, is something where there is no apparent impending motion. And what this means is the object's not about to start sliding. So if this is our block and we have the weight and the normal force, what this means is that some applied force is smaller than the maximum limit of F mu. In other words, the force applied is less than the max allowable friction force, which is F mu, which we can calculate using Fn times mu. And what I want you to think about here is, just like if I change the weight, the normal force changes. Just like if I change the applied force, the reaction friction force changes up to a limit. When we get to that limit, we end up at a type 2, which is where we have impending motion at all points of contact, because here with our particle system, that's really all that is able to happen. And so what I mean here is that we have reached the point where for a given weight, which produces a given normal force, the applied force F is exactly equal to F mu. In other words, we've hit the limit. F is equal to F mu, which is still calculated using Fn mu, and in this case, since they're static, these would both be mu s. And what this means is if I increase F any further, this thing's going to slide, and we would switch over to mu k. The third possible behavior is impending motion at some points of contact, and that only really happens in rigid bodies, so we're just going to table that one for now. The last thing that I want you to think about with all of this is that we still have the exact same 4 steps to solving any statics problem. We're going to draw the free body diagram. We're going to write the force balances, and we have one new relation that we get to toss into the mix, which is that the friction force is equal to the normal force times mu, and that's either K or S depending on the situation. Geometry comes next, right? Breaking things into components. And then lastly, doing some algebra. And now we can solve for whatever's unknown. Maybe we don't know the friction coefficient, right? Actually, this ramp is how they measure that coefficient for 2 different materials. We take the ramp, we increase the angle until the thing starts sliding, and that tells us what the coefficient is for those 2 materials on each other. So, anyhow, follow these 4 steps, and once again, you will never find yourself stuck as long as you remember that this equation, F mu equals Fn times mu, is the upper limit on the force, and it could be anything smaller than that, just like other reaction forces adjust according to the applied loads that they're experiencing.